I hope everyone's doing well. I'm Mr. Rich. Thank you for joining me for this video. We are looking here at solving this style of non-homogeneous or inhomogeneous differential equation, second order, where your function is not equal to 0, because then it would be a homogeneous. Here we're looking at non-homogeneous. Ordinary second order differential equations where the f of x is a particular variety and it will be an exponential. And we can better represent it as e to the power of kx. And that can be a positive or minus exponent. So that's what we have to look. We've already looked at a video where the function was either a constant or it was a linear term or it was a quadratic term. Here we're focusing on this, the exponential term. Your second order differential equation is equal to something other than 0 and it's equal to an exponential term. So it's a non-homogeneous second order differential equations. How do we solve this? I will show you 3 very specific examples to help you navigate this style of question. Second order derivative, first order, your basic y and your function over here, keep all of that in mind. When you are looking at something like this where the function is looking like a e to the power of like an exponential, then what you are going to use is this, a e to the power of kx. Notice I have a positive exponent, I'm using a positive. If you have something which looks like e to the power of minus kx, then you will use a e to the power of minus kx. Positive, you use positive. Negative exponent, use negative exponent. But these are the items you use to solve your differential equation. Keep in mind your general solution is made up of a complementary function and it's made up of a particular integral. You have to do both of these parts. This is coming from your homogeneous techniques. This right is coming from your evaluation of your function f of x, which is after the equal sign. So remember all of that. Let's start here with an example. Let's look over here at this first question. We have y double prime minus 2y single prime minus 3y equals 2e exponent minus 3x. It's non-homogeneous, equaling to a function which is an exponential. It's not equal to 0. We're going to start here with this, the complementary function, and you can do that by focusing here and treating it as a homogeneous. We have over here y is equal to e to the power of rx. Then the first order derivative is r e to the rx, and the second order is r squared e to the rx. You have to bring all of this into play. You will bring it into the template you have over here, r squared e to the rx minus 2r e to the rx minus 3 e to the rx is equal to 0. Equal it to 0 because it's going to help you out. E to the power of rx, you're looking at r squared minus 2r minus 3 equals 0. When you take this on the other side, it zeroes out. You're left with this. Your factors are r minus 3 and r plus 1 is equal to 0 and r is equal to 3 comma minus 1. You know when you're bringing this to real solutions, your template is going to be y is equal to a e to the power of 3x plus b e to the power of minus x. And that right there is done. What we have to worry about now is determining the particular integral from this, and I will show you the procedure, and it's not hard. I will, however, make one little modification to what I said earlier. Remember when I said at the very beginning, if you have a function which is exponential, y is equal to e to the power of kx, then you can use a e to the power of kx, and when you have y is equal to e to the power of minus kx, you can use a e to the power of minus kx. That's true, but you might as well use c e to the power of kx, and here you might use c e to the power of minus kx only because we're using a's and b's over there, so we can just have a different letter and you can run with that. But technically the difference is negligible because you're looking here for a value, an actual value, and the letter goes away. But I will use c over here instead of a, what I said earlier. So when I'm looking at this, you're not using 2 right away in terms of the template, but you're using it to help determine the value of the constant. I have y is equal to c e to the power of minus 3x. The k is exactly equal to what you see right over here. Here's my k, because we're looking at c e to the minus kx. K here is equal to 3. So run that through. If y is equal to this, the first order derivative is minus 3c e to the minus 3x. The second order derivative using the exponential templates will be 9c e to the power of minus 3x. Then you run that right here. You have here your second order, which is 9c e to the power of minus 3x. Minus 2 times minus 3 is a plus 6c e to the power of minus 3x. Minus 3 y is here, c e to the power of minus 3x is equal to, now you're bringing the 2 e to the power of minus 3x. If you divide everything by the exponential, it all goes away. What you really have left is a 9c plus 6c minus 3c is equal to 2. 9 plus 6 minus 3 is a 15 minus 3, which is a 12. C is equal to 2. C is equal to 1 over 6. Now we can determine our particular integral function, and this is how you do it. You already have your template right here. You know what your C is, 1 over 6. It's 1 over 6 e to the power of minus 3x. Now we have our complementary function determined and we have our particular integral determined. All we have to do is present the general solution, and we will. Our general solution is what? Y is equal to your complementary function a e to the power of 3x plus b e to the power of minus x plus your particular integral 1 over 6 e to the power of minus 3x, and we are done, and it should be good. This right here is my complementary function. This right here is my particular integral a e exponent 3x plus b e exponent minus x plus 1 over 6 e to the power of minus 3x, and we're good. Let's go to the next question. Question number 2, y double prime minus 9y single prime equals e exponent 2x. Before we solve this, let me digress a little bit. When you want to post your general solution, you can say y and subscript gs with regards to the x variable is equal to something. If you want to post only a complementary function, you can say y with respect to this complementary function, subscript, and x variable is equal to something. If you want to post only a particular integral, y with the subscript pi and the x variable, and the x variable could be a t variable, any variable, but you see the gist over here. General solution, your complementary function, your particular integral. These are different ways of posting your answer. This is part of your solution, this is part of your solution, this is your full solution. Let's solve this. We'll start with the complementary function first. You know you always have to do y is equal to e to the power of rx. Some people use m, some people use r. Then the first order derivative is r e to the rx. The second order derivative is r square e to the rx. And you post it right over here. I have r square e to the rx minus 9r e to the rx is equal to 0. When you're solving the complementary function, you're looking at your original equation, you're treating it as a homogeneous, and you go from there. You can isolate e to the power of rx. I have r square minus 9r. When you take the e to the rx on the other side, it zeroes out. You can isolate an r. I have r parentheses r minus 9 is equal to 0. R is equal to 0 comma 9. Or you can say 9 comma 0. It doesn't matter how you put it, but either way it's fine. You have a complementary function over here. You can do y with the subscript and the x variable if you want, but I'm not doing that. I'm not getting too technical. I'll just write cf. My complementary function here is either way. You can do a e to the power of 9x plus b e to the power of 0x. 0x is a exponential to the power of 0, which goes away. Or you can say a e to the power of 0x plus b e to the power of 9x, in which case you're looking here at a plus b e to the power of 9x. Either of these are fine. It doesn't matter. Order does not technically matter over there because you're doing 0, 9 or 9, 0. I'll stick with what I have at the top, a e exponent 9x plus b. The exponential term going away because it became equal to a 1 is irrelevant, and it doesn't matter. It doesn't spoil your solution in any way. Let's find our particular integral. We'll focus right over here. I know y is equal to e to the 2x, which we would say we're looking at a e to the 2x. I also said we can do c e to the 2x. We're using a different letter. My derivative with that is going to be 2c e to the 2x. My second order derivative is going to be what? 4c e to the 2x. You plug them right here. I have a 4c e to the 2x minus 9 times this 2, which is an 18, right? 9 times 2 is an 18. C e to the 2x is equal to e to the 2x. So continue this algebra through. You have here 4c minus 18c is a minus, 14c is equal to 1, c is equal to minus 1 over 14. My particular integral is going to be minus 1 over 14 e to the power of 2x because the template was c e to the 2x. We determined our c, we already have e to the 2x. Put them together and you have it. Now we just have to post our general solution by combining the complementary function and the particular integral, and we'll be done with this question. My general solution, which you know is a y is equal to, is a e to the power of 9x plus b minus 1 over 14 e to the power of 2x. This right here should be a correct answer. This part right here is my complementary function. This part right here is my particular integral, and it should be a correct answer. This question has been completed. Let's look at our last one. This is it. Y double prime plus 2y single prime plus y equals exponential. We're going to determine our complementary function first by focusing on this. We're looking over here at, y is equal to e to the power of rx. The first order derivative is r e to the rx. Then the second order derivative is r square e to the rx. You plug away. I have a r squared e to the rx plus 2r e to the rx plus e to the rx is equal to 0. You're always equaling it to 0 because you're treating that part, the complementary function determination, as homogeneous. You have here r squared plus 2r plus 1 because you've isolated e to the rx is equal to 0. You take it on the other side and it zeroes out. I am looking at r plus 1 times r plus 1 is equal to 0. Therefore, r is equal to minus 1 and minus 1. You have two real solutions, but they're identical. Now think back to how you write these out. You're not going to write these out as y is equal to a e to the minus x plus b e to the minus x, because if you think back to when you have identical solutions and you have one real solution, you make a modification. What's your modification? It's a e to the power of minus x plus bx e to the minus x. That right there is our complementary function which we will use. So when you have identical solutions, you bring in this x over here with one of your constants, and that creates your answer. So that's something you have to remember. Now what we have to do is determine this. If y is equal to e to the x, that's going to be viewed as c e to the x. That's what we use. It looks like e to the power of kx, we use a e to the x, or we use c e to the x, either or. I'm using c e to the x. That's my y. Then my first order derivative will be c e to the x. My second order derivative is again c e to the x, because the basic exponential has a derivative which is equal to the original function. Plug away. I have a c e to the x plus 2c e to the x plus c e to the x is equal to e to the x. You can isolate e to the x. I'm looking at a c plus 2c plus c is a 4c is equal to e to the x. Push the e to the x on the other side. I have a 4c is equal to 1. c is equal to 1 over 4. My particular integral will be represented in this template where I have the value c, 1 over 4 e to the x. Now what we have to do is bring our general solution into the picture and you're done. My general solution for this second order differential equation, non-homogeneous or inhomogeneous, is equal to a e to the power of minus x plus bx, don't forget this x, e to the power of minus x, only because we had two solutions but they're identical, so we have one real solution, plus 1 over 4 e to the x. Here's my complementary function part. Here's my particular integral part, and in combination these are your general solution for that differential equation. This right here is part of your solution, this here is part of your solution, but this here is your full solution, and this is it, a e exponent minus x plus bx e exponent minus x plus 1 over 4 e exponent x, and we are done. Keep in mind the exponential variety of these inhomogeneous second order differential equations are easy. You're either using c e to the x, or you're using c e to the power of minus x, or you can do a or a, it doesn't matter. But this is what you're using and running through to do your particular integral determination. Your complementary function is always coming from your homogeneous techniques. Thank you for watching. Have a good day.